Got it? Right. So in today's class, I'm going to teach about stability analysis. Right. So in last few classes, we were discussing about signal flow graph and the block diagram reduction. What was the main advantage of, or what was the use of solving the problem using signal flow graph and block diagram reduction? We were able to get the overall transfer function of the system. Using signal flow graph, we will be able to get the overall transfer function of the system, as well as using the block diagram reduction, we will be able to get the overall transfer function of the system. Now, from that, we can do the simulation, because why do we need to do all those methods is that we can use it for simulation purpose, whether the system is under controllable or not, right? So as well as we can able to check the stability analysis also using theory method, right? So there are Routh method is available, which will be used for checking the stability, and Bode plot is available, Nyquist plot is available. These are the techniques that will analyze the stability of the system, right? So when you get the overall transfer function of the system, C of S divided by R of S, you might have got two equations. One is numerator equation, the another one is the denominator equation. Let's say that is starting with the third order equation S cube, right? So this is starting with S power 4 and it goes on like this, right? So now to check the stability of the system, you can just take the denominator equation and you can apply the Routh method, then the stability can be analyzed using, then the stability of the system can be analyzed. I repeat, we have a signal flow graph and block diagram reduction. The method will give you the overall transfer function of the system. From the transfer function, we will have numerator equation as well as denominator equation also will be there. So this denominator equation is called characteristic equation. This characteristic equation, if you are analyzing this equation using Routh method, then the stability of this particular system can be analyzed, right? So now this, if I have a S power 4 equation, how many roots will be there? How many roots will be there for that equation? 4 roots will be there, right? Another point is that it is a S domain, because we are by taking the Laplace transform, we are converting into a time domain into a frequency domain. So S is nothing but your frequency domain. So in the S plane, if you are plotting, the graph that I have drawn is a S plane. So this is our imaginary axis j omega, and this is our real axis sigma. Okay. So now when you solve this particular equation, as you people told, it is a fourth order equation, you will be having the 4 roots will be there. So just by seeing, so if you get these 4 roots, if all these 4 roots are lying on the left side of the S plane, as I said, this is the S plane, imaginary axis j omega, real axis sigma. Now if you are plotting these 4 roots if all these roots are lying on the left half of this S plane, then your system is stable. Got it? If any of these roots is lying on this side, you have 4 roots. If any of these roots are lying on this right side, then the system is unstable. Okay. So even the roots are lying on this imaginary axis, then the system is said to be marginally stable. So the roots lying on the left half of the S plane is called, S plane is stable, right half of the S plane is the unstable system. The roots that are lying on the axis, imaginary axis, is marginally stable value, right? So to get all this roots value, right? So what we supposed to do is that we solve the equation and we get the roots of that particular thing and we go on for plotting it, right? So instead of doing that plotting, what we do is that we use the Routh method for analyzing, right? So we will have to use the Routh table. We will have to make the Routh table. by seeing the Routh table, we will have to tell whether the system is stable or not. Okay. Now, we will see some of the roots. If yeah, right. Okay. So it's not that much visible, I guess. Right. So here, what is there is you have got S plus A, some equation like A divided by S plus A. Now, as I said, you have got a transfer function with the numerator constant value A, denominator is S plus A. So, what is your roots for S? It will be S is equal to minus, say, if you are plotting in your S plane, your roots will be lying on the left half of the S plane. If the roots are lying on the left half of the S plane, then the system will be stable, right? Now, if you have got an equation like A divided by S minus A, then S is equal to plus A. So, if you have got root as S is equal to plus A, then your roots will be lying on this side, right? So, this is for S minus A and this is for S plus A. Now, looking at this diagram, right? So, this is S plus A, your root is S minus A. So, for this particular input, your output will be like this. That means you will get a settling point. I repeat, we have a equation that is A divided by S plus A. If that is a system, means your output will be like this, right? So, if your output is like this, you will get a settling time or settling error, right? So, we will be able to get some output. This is my point. We will be able to get this output. Now, if you have equation A divided by S minus A, your output will be like this. Will it end? No. It will be exponentially increasing. We will not be able to get the output. So, the system will be unstable. I repeat. So, if your root has got S is equal to plus A, then it will be lying on the right half of the S plane. If it is lying on the right half of the S plane, your plot is going to be like this, right? So, it is exponentially increasing. If it is exponentially increasing, you will not get any settling, right? So, as far as we have analyzed, right? So, this is the system, means your waveform will be settled like this, right? So, if it is settling, then the system is stable, right? So, if you are not getting the output like this, then the system is unstable. For a input A divided by S plus A, it is a decreasing one, so you will get an output. So, from the graph, you will be able to analyze it, right? So, if you get that output, means the system is stable. For a value of A divided by S minus A, it is root is S is equal to plus A. So, for that, your output is going to be like this. You will not be getting any analysis output from the output graph. So, the system is unstable. Okay. So, more in detail about for all other input, how the system is working also is given in this particular PPT, right? So, we will also be discussing about in the next class also for different input, how your output is going to be react. So, for this input, your output of the system will be like this, then the system can be stable. Why? Your root is S is equal to minus A. S is equal to minus A will be lying on the left half of the S plane. The system will be stable. Here your system is A is equal to S minus A, your root is S is equal to plus A. For that, your output will not be stable, right? So, the system will be unstable. For various input, how your output system is going to be react also is given in this particular PPT. We will also be discussing about in the tomorrow's class also, right? Okay, so take down the problem, type 1. check the stability of the system, check the stability of the system. Using Routh curves, check the stability of the system using Routh curves method. So as I said earlier, it is the denominator equation in the overall transfer function of the system, right? So because when you get the overall transfer function of the system, you will be getting the equation like this, I guess. For an example, we will be getting the equation. We used to get equation like this for up to G6 also we were getting, right? So as I told earlier, we may be having some equation for G1 also, as well as for G2 also we will be having. Then the H1 also is 1. So if you are substituting all these values here, G1 is equal to 1 divided by S plus 1, G2 is some system value. If you are substituting over here, then you will be getting some equation like this, right? So in this overall transfer function of the system, you can take the denominator equation alone and you can apply the Routh-Hurwitz method. Okay, so this equation only I have. For some other system, that equation I have written it over here, and we will have to check the stability of the system using Routh-Hurwitz method. Okay. Right. So what is the order of the system? It is the S power 4. So that means 4 roots will be there. Using the Routh table, we will have to make the Routh table, and we will have to say how many poles will be on the left side and how many poles will be on the right side, right? As I said, we will have the two equation, one is numerator and another one is the denominator. So roots in numerator is called zeros. I repeat, the roots, maybe whatever roots that are there, that we call it as a zeros. So the denominator roots are called poles, because while I say, I might have said roots as well as poles. So the denominator roots are called poles. Okay. So using the Routh, we will have to make the Routh table, and we will have to say whether the system is stable or not. Okay. So it is the fourth order system. So write it like S power 4, S3, S squared, S1 and S0. Since it is a fourth order system, we will have to write it from S power 4, S3, S power 3, S squared, S power 1 and S0, that is constant value, right? So when you make this particular table, first write S power 4, then write S squared, then write the constant value here. Okay, so write only the coefficients of all this. So for the first one it is 1, S squared it is 18, over here it is 5. For the S power cube rows, you will have to write these two, 8 and 16. Got it? First step is that, since it is a fourth order system, writing S power 4 like that. Then the next thing is that writing the coefficient near S power 4, that is 1, writing the coefficient near S squared 18, then finally the constant value. For the next row, we will have to start it with S cube. So the coefficient of that is 8, and for coefficient of S is 16, right? So the next step is that, here if you have got, in this particular row, you have got 8 and 16. So commonly you can divide by 8. Okay. So if you are dividing like this, then it becomes 1 and 2. Without doing it like that also you can solve, but while doing the multiplication, if you have the values like 16, then the complexity of the problem will be there. So to avoid that, you can take a common value. 8 and 16 was there, I am taking it as a 1 and 2. Okay. So the first step is that you will have to multiply with 1 into 18, 1 into 18. Second one is minus of 1 into 2, minus of 1 into 2. The whole divided by this value 1. Writing 1 into 18 minus 1 into 2. Okay, so this will be the first one that you will have to multiply, and minus of, that's the second one, 1 into 2. Right, so if you are solving it, what is the value you will get? 16. So the value that you get, you will have to write it here. Get it? So by solving these 4 values, what is the value that you get? You will have to write here. Next, this whole thing has to be multiplied with this one. So 1 into 5 minus, there is no values there, minus 1 into 0 divided by 1. So what is the value you will get? 1 into 5 minus 1 into 0 divided by 1? 5. Got it? So the second step is that you will have to multiply 16 into 2. So to get this element, you will have to multiply 16 into 2 minus of 1 into 5 divided by 16. Calculate the value and tell me. 16 into 2, 32 minus 5 divided by 16. 27 divided by 16. 27 divided by 16, 1.3. 1.7. Okay. So 1.7 will be. Now you don't have any other elements over here to multiply. So you will get this term only. I repeat. So for getting these two, you had 1 into 18 minus 1 into 2 divided by 1. So for writing this value also, you had 1 into 5 and 1 into 0. 0 was not there. So 1 into 5 was there. So we were able to multiply and get this value. But for the next time, 16 into 2 minus 1 into 5, we were getting 1.7. There is no element is present over here to multiply. 16 into 0 minus 1 into 0, the value is going to be 0 over here. So no need to calculate it. Now multiply 1 into 7, sorry, 1.7 into 5 minus 16 into 0 divided by 1.7, value is 5. Got it? So this is a Routh table we have made. Just by analyzing this Routh table, we will have to say whether the system is stable or not. Okay. So now here, if you are looking at this, this is also a positive value, plus 1 and plus 16, plus 1.7 as well as plus 5. Okay. So there is no sign change. Plus, 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 plus as well as this also is plus. So now if you are looking at this and all these values are positive, so that means it is a fourth order system. All the 4 poles are lying on the left half of the S-plane. Then the system is stable, right? So we don't need to say the pole location or where it is exactly lying. We will have to say whether it is lying on the right side or left side. The roof poles is lying on the left side, stable, right side unstable, lying on the axis, it is marginally stable. Now here you have got all these are all positive. There is no sign changes there. Negative values are not there. So then all the poles are lying on the left half of the S-plane, then the system is stable, right? So instead of this, if you have got a values like 1, then 16, 1.7 and 5. So if you have got a values like this, means this is positive. From plus to minus, there is a 1 sign change. From plus to minus, 1 sign change. Minus to plus, second sign change is there. Then plus to plus, plus to plus only. So you have got 2 sign changes over there. So if you have got 2 sign changes, you will have to write it like it is a fourth order system. So 2 poles are lying on the left half of the S-plane and remaining 2 poles are lying on the right half of the S-plane, right? So you have got poles lying on the right side also. Then the system is unstable. Got it? Just by solving it using the Routh table, right? So forming it also very simple. Use this 1 into 18 minus 1 into 2, right? So then you will be able to make this table also by seeing the first column alone, right? So just by analyzing the first column alone, we will be able to say how many poles will be lying on the left side and how many poles on the right side also. We will be able to analyze it over there, right? So if there is sign changes present over there, then there are 2 sign change, plus 2 minus 1, minus 2 plus 2 sign change. So 2 poles will be on the right side, remaining 2s are on the left side. Then the system is unstable over here, right? So write the result for the problem number 1. By analyzing the column 1, there are no sign changes. By analyzing column 1, there are no sign changes. Therefore, all the 4 poles will be lying on the, left half of the S-plane, Then the system is stable. Okay. So now, while we solve, figure all this problem, we will be able to solve. This is type 1. While you make the Routh table itself, you will be able to face in 3 types. Okay. So this is another type. So what would happen is that here we have got 2 elements, right? So instead of these 16 and 5 values like that, we will get 0, 0 over here. The whole row will become 0 in this particular problem, right? So if you get a whole row as 0, will you be able to get the another row value? No, because you are multiplying with the like that, right? So you will not be able to get the another row, right? So when you get a row full of 0, what you will have to do, right? So this problem will explain that. The next problem will tell you only one element has become 0. In this particular thing, instead of 16, if it is 0 comes, what we will have to do, right? So these are the 3 types we are solving, right? So in the second type, we have got a 6th order equation. So we will have to start the values from s power 6, right? So the table start with s power 6, 5, 4, okay. So to make the first column, we will have to take all this even order values. Okay. So just write the coefficient near to s power 6, it is 1. Coefficient near s power 4, it is 8. Coefficient near s squared, it is 20. Coefficient, the last is constant value is 16. Right. So for the next row, we will have to take the values of all the odd orders, right? So first one, it is s power 5, it is near, coefficient value is 2, it is s cube, it is 12, then s, it is 16. Right? So the first step, what we'll have to do is that we will have to get this element first, right? So to get that element, we will have to multiply 2 with 8, 2 into 8 minus 1 into 12 divided by 2, right? So here also in this you have got 2, 6, 12 as well as 16. You can divide by 2 all this value, right? So you can do it like that also without dividing by some common value also, we will be able to do it, right? Okay, so as per this, 2 into 8 minus 1 into 12 divided by 2. What is the value you will get? Okay. So for the next element, what is the next element you will get? 12. Next. Okay. So you have got the s power 4 row also you have got. Now if you multiply with 2 into 12 minus 2 into 12 divided by 2, you will get 0. For the next value, 2 into 16 minus 2 into 16 divided by 2, you will get 0. So this whole row will become 0 over here if you solve, right? So now what we will have to do is that you will have to write out this particular equation, take the differentiation. You have got a fourth order equation. If you differentiate once, you will get, you have s power 4 is there, you differentiate once, you will get s power 3 equation you will get, right? Because from s power 4 to get the s cube equation, when we try to solve, this row is becoming full of 0. So write out this equation, differentiate it once, right? So if you differentiate once, s power 4 equation, if you are differentiating, it becomes s power cube, then that equation can be written over here. Okay. So now, while you write this particular equation, particular table, how you wrote s6, s power 4, s squared, then the constant value, right? So now you have got a s power 4 equation, then this value will be 2 s power 4, this will be plus 12 s squared plus 16 is equal to 0. When you write out that particular equation, you will have 2s power 4 plus 12s squared plus 16 is equal to 0. Right? So we will have to differentiate this equation. If you differentiate this equation, then it will become 8s cube plus 8s cube plus 24s is equal to 0, right? So now this particular equation can be written over here. Okay, so if you are writing, it becomes 8 and 24. We are solving, we are taking the differentiation over here, right? So then the order of the system is reducing, then we are writing it here. Now you go on solving to get the s squared. Now multiply 8 into 12 minus 2 into 24 divided by 8. Tell me what is the value you will get? 6. Okay. 6 you will get over here. To get the another element over here, multiply 8 into 16. 8 into 16 minus 2 into 0. 8 into 16 minus 2 into 0 divided by 8. The value will be 16 over here. Right? So now you don't have any other elements to get over here. Now go on solving for s power 1. Multiply 6 into 24. 6 into 24 minus 8 into 16 divide by 6. 2.6. Next value, the value will be 2.6 into 16 divided by 2.6, it will be 16. Right? So in this particular problem also we have made the Routh table. Okay. So if you are looking at this particular column, all these are all positive, then you will say the system is stable. But just like this problem, we will not be able to say here, because we have differentiated this equation, and we have got this table. According to this, all the poles are lying on the left half of the S plane, because all the 6 poles will be lying on the left half of the S plane, right? So since you have differentiated this particular equation and you have solved, what you do is that you will have to take this particular equation and you will have to find the roots of this equation. Just substitute S is equal to x squared, then the equation will become S x squared plus 12x plus 16 is equal to 0. Okay. Now find the roots for this particular equation and write. What are the roots? You will get x is equal to -2 and -4. Just check. Just listen, I have written this equation and I have substituted s is equal to x squared. Okay. Sorry. S squared is equal to x. I have written s squared is equal to x. Then the equation will become 2x squared plus 12x plus 16 is equal to 0. Now find the roots for this equation. -4. Right. So substituting the above equation, then your roots of this will be, you will have plus of -4, comma, minus of -4, comma, plus of -2, comma, minus of -2. We have got x as -4, comma, -2, right? So substituting s squared is equal to 2, we will be having 4 roots. This is the second order equation, we have got 2 roots. This is a fourth order equation, we are supposed to get 4 roots, right? So substituting again s squared is equal to x, right? So this will be in the root form. -4 is there, we will have plus root 4 as well as minus also. For the same thing, we will have plus as well as the minus also we will be getting. Now we have got 4 roots. Since if you are inside the roots, if you have got a minus, then we will call it as a j, right? So as I said, we have got pluses there, plus j 4 minus j, sorry, this inside the root, so it will be 2, right? So plus j 2 minus j 2, this will be plus j root 2 minus j root 2 will be there. We have got 4 poles, we have got 4 roots like this. Now if you are plotting these 4 roots in the S plane, right? So you will be having 4 roots will be on the imaginary axis. All these 4 roots, if you are substituting it over here, all these 4 roots will be on the imaginary axis, right? So now we will be able to say, according to the Routh table 1 first column, all these are all positive signs, the system will be stable. Since one row became 0, we have taken out that particular equation, differentiated once, we have finished our Routh table. Now you will have to take out that particular equation, find the roots of for the same, right? So we have got s is equal to all these roots or poles. All these poles will be lying on the imaginary axis, because inside root we have got -1, right? So minus we have got, so it will become j, this will also be J, this will also be J, this will also be J. So we have got J means this is J omega sigma over here. This is real parts and this is imaginary axis. Real axis and imaginary axis. All these four poles are lying on the imaginary axis, right? So the system is marginally stable, right? Write the result. First one, the system is marginally stable. And the result, write the first point, the system is marginally stable. Second point, two poles are lying on the left half of the S-plane. Two poles are lying on the left half of the S-plane. Remaining four on the imaginary axis. Remaining four lying on the imaginary axis. Okay, so we will solve the third type also, right? So that you have understood this, we will solve the third type also, right? So form the Routh array for S power 5 and S power 4. First element will be 1, second element will be 2, third element will be 3. For the S power 4 it will be 1, 2 and 5. For the first row will be 1, 2 and 3. Second row will be 1, 2 and 5. Go on solving. We will have to multiply by 1 into 2 minus 1 into 2 divided by 1, it becomes 0. For the next value it is 1 into 3 minus, 1 into 3 minus 1 into 5 divided by 1, it is minus 2. Right? So when you have here in the previous type, you have got a full row was 0, all the elements were 0. In this particular row, you have got only one element as 0, right? So if you have got only one element as 0, take is as a sum variable E. Take it as a sum variable and now go on solving. Multiply E into 2,